All right, welcome back to the LeetCoding challenge. This is day 10, min stack. Today we're going to be designing a data structure instead, and it's going to be a stack with a weird quirk that you always know what the minimum element is because we can retrieve it in constant time. They give us an example, so let's try working out the example and figuring out how to build our data structure. So in this example, we're given, some numbers, -2, and then 0, -3. They ask us what the minimum of this so far is, and then we'll say, it's -3. And then we pop it. So you can imagine popping off the top of the stack as something like this. So if this is our, sideways stack, like that, they ask us to pop off the top of our stack. And then they ask, what is the top of our stack? And the top of our stack here will be 0. And then they ask again what the minimum is. So the minimum at this point is not 0, but rather -2. And we're going to try and build a data structure to support this. So we might notice that because we want minimum to be done in constant time, we should always know what the minimum is at all times. That way, when the user requests it, we can give it to them right away. Now, in the case of -3, -3, we were lucky enough that it just happened to be the top. So we could these turned out, minimum and the top turned out to be the same thing. But as you can see, as we popped it off, it was no longer the case here. So one way we can do is we can just track it at all times. So if this is our stack, these are our values, this will be the minimum. So we're saying at this point in the stack, -2 is the minimum that we've seen so far. And, if we included more, 1 here, it would still be -3. If we did -9, then from this point on, everything is -9. And this kind of keeps track of it. Okay, so from here, we have a couple of choices. We can, create a new class that holds this. Maybe a new class node that knows our value in the stack and also our minimum. And then we can feed this node into any existing class that supports the stack paradigm. So, we could feed this into a stack. We can feed this into an array deck, so array double-ended queue, because they both support adding last and removing from the last. Or something interesting we could also do is we could visualize this as a sort of linked list instead and build our own if we wanted to. So where each node would also have next, and it'll point to the next node in our list, and their next node and next node and so on. Okay, so we have a couple of choices. For today, I'm going to choose, let's just use one of these. We have our array deck. Array deck typically on normal usage, you can actually see from their website if you just look up array deck, that typically this class is likely to be faster than stack when used as a stack and faster than linked list when used as a queue. So we'll use this. Okay. Let's try programming this. So we need our new class, public class node that will keep track of what the current value is as well as the minimum. And we'll give it a constructor. So public node int value int min. Oh, that's weird. This dot min equals min. Okay, so there is our class, and our class will also have its own array deck, which takes in the node, and this will be our internal stack. Cool. And then we can initialize it. And then let's do some of the easier ones first. So I guess we have top. So what we can do is we can, let's see, we want to peek at the top. So stack dot, let's see here, we have peek last, retrieves but does not remove the last element, or returns null if this deck is empty. Now we can see here that in the definition we are returning a primitive, so it should always be something. So that kind of gives us a sense that if the programmer calls top with nothing in our stack, we throw an error because there's just no plausible value. So if we return an integer, then we could return a null integer in this case. But since we're returning an int and it has to have a value, we're just going to throw an error instead. So instead of this peek first, which returns null, we can just call another one, which is, let's see, get last. So what get last will do is it will retrieve the last element and it throws an exception if this deck is empty. So it looks like that's the one that we'll want. Okay, so stack dot get last. So we have our top, and then we can return top value. Okay, and then let's try minimum. It'll be the same thing. Stack dot get last, and then this will return the minimum instead. Okay, so here we have pop. We can also just do remove last here. And, you know, if the stack is empty, then here we'll also throw an exception because remove last throws an exception. And then we'll also have push. So stack dot add last. We'll add a new node with the value x. But now, what do we put for this minimum? So this minimum, you know, it's either what the top is already, or is our new x, depending on which one is smaller than the other. And here we have to watch out for a case where what if top doesn't exist? We don't want to throw an error here because it just means x is our new one. So what we can do is if stack dot size is equal to 0, we have the case where nothing exists in our stack yet. In this case, we can confidently add a new node where the minimum is itself. For the other cases, what we'll do is now we need to compare. So our minimum is equal to whichever one is smaller. It's either us or it's whatever is at the top. So we know that this must return something now because our size is greater than 0. And then we'll get the minimum here. And then again, we'll add last new node x at min. Another way, if you want to be cleaner about this, is you could have this code here. You could have int min equals x, and then you can say if stack size does not equal 0, then we reset min to be the minimum of either x or get last min. Up to you how you want to phrase this. Those two are equivalent. Okay, so let's give this answer a try. And it seems like it works, so we'll submit. and it's accepted. Nice. So from here, we used an array deck. We had our own class that kept track of value and min at all times. And when we push, this is get last is a constant time operation, add last is constant, remove last is constant, top is also constant, and min is also constant. So we've created a data structure that gives us constant time for all of these, which is what we want. Okay, so that's the end of day 10, and I'll see you on the next one.